All right. Well, chapter 6 has been an extremely long chapter. I've kind of deliberately chosen to take my time and not cover it in as much of a rush. But okay.
Sorry, I have a slow clap.
Oh, okay. But today, presumably, it'll all come to an end.
He said he's not coming.
Oh.
He forgot to email you.
Okay. Well, good.
Or he meant to email you.
Well, good that I know. Not to,
He said please send his apologies.
okay.
But that's funny.
Okay. So, we were just doing a case where the PDE was non-homogeneous. So you'd have like UT plus LU equals some function big F of xt. But now we're going to look at a different kind of non-homogeneity. Non-homogeneous boundary conditions. Okay. All right. So what I'm going to do is I'll start out with an example, and by the end we'll have a. Oh, this is a problem. I seem to have completely forgot to include one of the examples. Hold on. Which is really weird because I could have sworn that I actually typed that up. Let me check.
Will you be time to go type?
Not in the middle of class. Oops, that's the wrong tech file. Well, that might be all we type for anyway, because I still have several pages of notes. Yeah, I really did forget to type it up, but it's weird because I have dim memories of working on it. Okay, but all it was it's just one of the examples from a textbook, so I'm going to. So I still might be able to do it, but it might be interesting having to do it on the fly. Okay. So I'll just get that open real quick. Come on. Okay, this is section. Come on. 6.6. Oh, I see. No, I did not actually work on this, but if time permits, then we'll do it. Okay, or at least the essential part. Okay, so even then I still have probably enough pages and notes to fill the 75 minutes. All right, so I'll start out with this example that I have worked out. So ut equals alpha squared uxx, where alpha is a constant. This is on the interval 0 to L. All right, and then we have Dirichlet boundary conditions, but now they're non-homogeneous. So at x equals 0, the solution is equal to a constant k1. And it'll turn out that for what we're doing, it doesn't matter whether it's a constant or some function of t. The procedure is the same. And then at x equals L, it's equal to another constant. And then we have initial data u is equal to p of x. Okay, so we can't just jump in and do our usual separation of variables and Fourier series thing, because we have to deal with the boundary conditions first. Our eigenfunctions, you might think, oh, it's going to be something like sine pi x over L, but that satisfies homogeneous boundary conditions. U is equal to 0 at x equals 0 and L. So here's what we do. I'm going to express the solution as a sum, and I can do this because the PDE is linear, and so are boundary conditions. And in this case, I can write u of xt as v of xt plus w of x, Now, normally I'd have wxt, but I don't need that in this case because boundary conditions do not depend on t. So at least we can get away with a function of x. Now, I'm going to write down the problems that v and w solve. Okay, so they both have to satisfy the same. So vt is alpha squared vxx. So v satisfies the same PDE as u. And then v has the same boundary conditions except homogeneous. And then for the initial conditions for v, it's going to be the same initial conditions as for u, except we're going to subtract off whatever our w is. Okay. And that makes sense because if u is equal to v plus w, then v is u minus w. So it makes sense that we would have that worked into the initial conditions. Okay, so this PDE, we know how to solve. That's what we've been doing. So we don't need to talk about that. Now, W is a, it needs to be a function that satisfies boundary conditions. Now, it's a function of x. We're going to make it a function that's linear in x. And the reason for that is, by making it linear in x, also it only depends on x. It doesn't depend on t. So wt is 0, because it doesn't depend on t. And also wxx is 0, because the second derivative of any linear function is 0. So in other words, it satisfies this PDE already. And we require W to satisfy, gotta make sure it's still recording. Oh, sorry, I goofed for those of you watching at home. There. Okay. So, imagine someone's going to be yelling at me for that while we're watching. Okay. So, we require W to satisfy the same boundary conditions as U. So, W of 0, T is equal to K1. W of LT is equal to K2. All right. Now, because the boundary conditions are linear, because U and W satisfy the same boundary conditions, their difference, which is V, satisfies homogeneous boundary conditions. So in other words, literally everything adds up. U, V, and W all satisfy the same PDE. The boundary conditions for V and W add to be those of U, and the initial data for V and W add up to be those of U. So now we just have to deal with this. What is a linear function in X that satisfies both boundary conditions, K1 and K2, at X equals 0 and X equals L, respectively? And for that, I'm going to explain this a little differently than most PDE textbooks do, because I'm a numerical analysis person, so I'm going to use a concept from that, because it comes in handy. It is known as Lagrange Interpolation. But we're just dealing with a very simple case of degree 1, so it's a lot easier to explain in that setting. Okay. Okay. So, the problem here is to find linear function wx so that w0 is equal to k1, wl is equal to k2. Now, years ago, the problem's what?
Sorry, did we do Lagrange or something with Lagrange Interpolation in 460?
460, yeah, 460.
460.
Yeah.
Okay, cool.
Yeah.
Polynomials.
Yeah, and
Yeah, okay.
yeah, and you'll see it again in 772.
Cool.
Okay, so good memory. Now, the problem of finding the equation of a line that passes through 2 points, that's a problem you've known how to do for a long time, like I think it's high school or something. But this is also something that Lagrange interpolation, you think of as a way to generalize that to a higher degree, where you have to fit more points with something of higher degree. But okay, so okay, I'm going to check my notation here. All right. So I can write Wx in this form. My first constant, k1, times L0 of x plus k2 times L1 of x. And these are called Lagrange polynomials. And they're constructed, they're defined to have certain helpful properties. So L0 of x, we want it to be equal to 1 when x is equal to 0, and 0 when x is equal to L. So that way, when we're plugging in our boundary points, x equals 0 or x equals L, we're basically selecting k1 when x is equal to 0. And then L1, and by the way, for your notes, I'm leaving a little space in here intentionally, so I suggest you do the same. So L1 should be equal to 0 when x is 0, and 1 when x is equal to L. So when you plug in x equals L, this will be turned on, this will be turned off, and you'll get k2. So, but the thing is, what we're doing is basically we're specifying for roots of Lagrange polynomials by saying where we want it to be equal to 0. In this case, it's linear, so there's only one root. So, I want this to be 0 when x is equal to L, so I can say x minus L. So now L is the root. But what if I plug in x equals 0? I want to get 1, but if I do this, I'm going to get minus L. So I can divide by 0 minus L. So when I plug in x equals 0, everything will cancel, and I'll get 1. So now I can simplify this. So this is L minus x over L. Okay. So that's that Lagrange polynomial. Here, same idea. I want it to be equal to 0 at x equals 0, so it's x minus 0, so that's the one root, divided by L minus 0. So you can see a pattern in how these are specified. So of course it simplifies to x over L in this case. So now I can finish my w of x. So it's the first one, L minus x over L times k1 plus x over L times k2. And actually this can be simplified, but because you can write this as k1 plus x over L k2 minus k1. Right. So this satisfies the boundary conditions. You plug in x equals 0, you get k1. Plug in x equal L, and you get k2. So then you can go ahead and solve for v as before. And what's going to happen is u of xt is v of xt plus w of x, and for this problem we know what v looks like. We know its general form because it satisfies homogeneous Dirichlet boundary conditions. So v is going to be a series, but v n, well, okay, because of a PDE we're going to have e to the minus alpha squared t, n pi over L squared t. So that just comes from a time-dependent problem. Because the eigenvalues are going to be n pi over L squared, like we've seen in this kind of problem before. And then we'll have coefficients, I'll call them phi sub n. So these are the coefficient, the Fourier sine series coefficients of phi of x, the initial data. Oh, actually, I need to include that as well. Dn minus wn. And then I need my eigenfunction, sine n pi x over L, plus, and now I can just add all my w of x. So k1 plus x over L, k2 minus k1. All right. All right. Now, if you plug in t equals 0, so this exponential goes away, then w of x is going to cancel with a series expansion of w of x, and you're left with phi of x. But that's what you want, because the initial condition is u of x0 is only phi of x. But this correction, w of x here, is meant to make sure that the boundary conditions are satisfied. Because this here is only going to satisfy homogeneous Dirichlet boundary conditions, because you have a sine n pi x over L. You need this added onto it to satisfy the original boundary conditions. Just for completeness sake, these coefficients, so phi n is inner product of sine n pi x over L with v divided by L over 2, inner product of sine n pi x over L with itself. And Wn, similar thing, so it's 2 over L, inner product of sine n pi x over L with w of x. Okay. All right. So that's how we solve that problem. So you're finding the simplest function possible that will satisfy the boundary conditions. If any, subtract it off. If any of a problem homogeneous Dirichlet conditions, then you can solve using everything else we've covered in this chapter. So any questions about this one?
Phi and the denominator, that's L over 2, right?
Yes.
So that came about from taking the inner product of sine n pi x over L with itself,
Yes.
right? Because
Yeah. Okay, and this is really old stuff, but I want to have it's reasonably self-contained. Okay. All right.
that's what we did first there, right? 6.1.
Yeah. And to let, also to a certain extent, chapter 5.
Also, yeah.
Yeah. Okay. Alrighty. Now, okay, doing on time here. Okay. Now, this is just one case, though, of Dirichlet boundary conditions where the actual boundary values happen to be a constant, but they could also be functions of t. So what I'm going to do is I'm going to show you an approach that is fairly general. Doesn't cover all the cases, but it covers a lot of them. And then I have an example that covers one of the important exceptions. So that way you can do whatever problems there are. Well, actually, hold Hold on, I thought I had another example in here. Oh, I do.
With
Good.
Neumann,
What?
maybe with Neumann boundary
Neumann?
Yeah.
I'm saving Neumann till the end.
condition. Okay.
Yeah, because Neumann is, yeah, it's one of the most important cases, obviously, but it's not handled by my general approach. So it tweaked a little bit. But now you do something that is neither Dirichlet nor Neumann. Okay. So now we have same PDE, same interval, and now our boundary conditions are more complicated. So we have some function a of t on the left boundary, x equals 0, and so the x equals 0 boundary condition is still Dirichlet, but the right boundary condition is not. So I have du dx plus some constant h times lt is some lower function b of t. So in terms of how we normally describe these regular boundary conditions, alpha is 1, beta equals
Bless you.
beta equals 0, okay. Gamma equals h, and delta equals 1. Okay. And then same initial data. Okay. All right, so now let's focus on the boundary conditions. So again, we're going to find a linear function, but this has to be wxt because the boundary conditions are time dependent. So we still want it to be linear in x. That satisfies these boundary conditions. Okay. So, w is going to have this form. A of t times, oh actually, okay. I can make it more general now. It's some function k1 of t, that's unknown, times the first Lagrange polynomial at x equals 0, so L minus x over L, plus some other unknown function of t, times the second Lagrange polynomial. Okay. Okay, and we're going to figure out the right k1 and k2 so that satisfies the boundary conditions. And for that, we'll just substitute this form into the boundary conditions. So w of 0t, what happens if we plug in x equals 0? What are we going to get?
K1 t.
Just K.
Yeah, just k1. Now, it's supposed to be equal to a of t. So that determines what k1 is. So that one has been settled. We just have to figure out what k2 is. So for that, we need to plug wxt into this boundary condition. So wx of xt is equal to, okay, a of t times derivative of this. What is the derivative of that?
-1
And minus 1 over L.
and then 1 over L.
And then here,
K2 t 1 over L.
yeah, k2 of t times 1 over L. Okay. And so now we can plug in x equals L into our function and its derivative. So we need dw dx of L and t plus h w of L and t. So that's going to be equal to, well, this actually is independent of x. So plugging in x equals L doesn't really do anything. So I'll fill that in. Actually, we can simplify it a little bit. 1 over L times k2 minus a of t plus h times this, where we plug in x equal L. But what do we get if we plug in x equal L?
K2 of t.
just K2 of t, because that's the nice thing about Lagrange interpolation. It selects one term or the other. The other is wiped out. So it's just K2 of t. And this has to equal B of t to satisfy the boundary conditions. Now everything here is known except for K2. So now I can just go ahead and rearrange this a lot to solve for K2. Actually, first thing I'm going to do, I'm going to multiply through by L because I don't like fractions. So we have K2 minus A plus HL K2 is equal to B is equal to L B of t. So now I can just rearrange this. Oh my god.
Oh.
Again, sorry to those of you who were wondering what was going on. So Abby, you can stop yelling at your screen. Okay. So here's what I've been doing for the last several minutes. Okay. Now, so we're going ahead and rearranging this to solve for K2. And think, I was just about to look at the computer to check to make sure that the computer was capturing the bottom of the board, only to find it wasn't capturing any of the board. Okay, I need somebody here to remind me, evidently. Okay, so, all right, so just by rearranging this is algebra at this point, we can solve for K2 of t. So it's going to be moving A of t to the other side. So A t plus L B of t divided by 1 plus HL. Okay. It's weird. Why do I have it written differently? L. Okay, LB of t. Hold on a second. Oh. Something's wrong. Okay. Or something's wrong in my notes. I need to find out. Okay. Because H of LT, sorry. Sorry, I didn't sort this out. I remember it's mistake in the notes or mistake in what I've written on the board. Okay, so.
The board looks fine.
Yeah, which means a mistake. That's really the case, and there's a mistake in the notes. Okay, so H W T is. Oh, I see what I did. Yeah, because I had something different written here on my notes, except terms cancel out, so it's still equal to this, and. All right, because what I have is, okay. So that's just my K2, and then I have LB over 1 plus HL, so that definitely matches up. And then I have, if I put this over a common denominator, I have minus HL A of t, just A of t. Okay, it's equivalent, but this expression is definitely the simpler, so we'll just go with that. All right, so now I have my W of xt is it's all this, but with K1 and K2 filled in. So it's A of t, L minus X over L, plus K2 of t, which is A of t plus LB of t over 1 plus HL times X over L. Okay. All right, and something strange here in the notes also. Okay. That's equivalent. Actually, yes, there's a mistake in the notes. Because in the notes, I just had A of t, I forgot the actual Lagrange polynomial. So I'll need to correct that later. Maybe I can simplify some of these other things. Okay. So now I have my linear function in X that satisfies the original non-homogeneous boundary conditions. But to finish things off, I need to do the same thing as before. U of xt is equal to v of xt plus w of xt. Now, so the thing is, I have w of xt. What about v? What problem does that solve?
Homogeneous.
Homogeneous boundary conditions. So vt is equal to alpha squared vxx. However, I need to subtract off wt. I didn't need to do that before because
Which is 0.
wt was 0. So technically it was subtracting off, it just was nothing to subtract off. And this just comes from the fact that everything's linear here. So ut is vt plus wt, uxx equals vxx plus wxx, but w of xx in this case is 0 due to it being linear in x. So that means that if ut is equal to alpha squared uxx, then that means that vt is equal to alpha squared vxx, which, okay. So another way of looking at it is, I want to derive this. Vt equals ut minus wt, but ut is alpha squared uxx, but uxx equals vxx. Okay. So there you can see in full where the new PDE comes from. All right. So that's so what you've done is you've made a trade. You've traded non-homogeneous boundary conditions for non-homogeneous PDEs. But we know how to solve non-homogeneous PDEs. That's the previous section. Okay. V satisfies homogeneous boundary conditions, so v of 0t is 0, and vx of lt plus hv of lt is 0. And as for initial conditions, v of x0 is equal to phi of x, the initial condition for u, minus w of x0. And that's just because u is v plus w, so v is u minus w. So you're just rearranging that. And you're plugging in t equals 0 throughout the whole thing. Because this is u of x0. Okay. All right. So this is a problem that we know how to solve for these boundary conditions. Doing separation of variables, eigenfunctions, expansions, and all that good stuff. And then you just add on w of xt at the very end, and you have your solution u. So any questions about that?
So v of 0t is 0 since it's ut minus wt.
So should I say again?
V of 0t is equal to 0 because a of 0 is...
Yeah, because U and W are both equal to the same thing at the boundary. So the boundary conditions,
The same thing, so that
So
they
they
cancel out.
that's the whole principle.
Right, okay.
So our final answer, we would write u of xt equals, we would, for w, we plug in
That,
that
yeah.
down here.
Plus
and-
what do you get from solving that equation?
Oh, okay, you didn't finish that. Gotcha.
So this is a problem we know how to do.
Oh, okay, all right, and but you plug in what you get for that for v, and what you get for, and that's your final.
Yes. Alrighty. Okay. Any other questions? Alright. See how we're doing on time. Okay. So now I need to cover at least as general a case as possible, which still doesn't cover Neumann. So someone tells me about that example, but I never did. I may not have time to do anyway. But it's in the textbook. So the textbook has certain scenarios, like if this is your boundary condition, here's your W. And this approach I'm going to show you covers all of those cases already, except the Neumann case, which is something all of its own. Okay, and look, I'm remembering to move the computer. Okay, so I'm putting general in quotes because it can't cover everything. So if we have general regular boundary conditions, so alpha u0t plus, so this is the same notation I've used for this before. T equals some function a of t, and gamma u of 0t, u of lt plus delta du dx of lt equals b of t. Now, what I found unfortunate in textbook is they use a of t and b of t also for boundary conditions, but they also work in the interval x going from a to b. So that's unfortunate, but so I'm just sticking with 0 and L because that's what we often do anyway. Okay, so we have w of xt have the same form as in the last example. Some function of t, L minus x over L, plus k2 of t, x over L. So the idea is, once again, to solve for k1 and k2. So we did that in the last example, but now it can show a more general approach. Okay. Now, so this means that we plug in x equals 0 and x equal L. Well, at x equals 0, we're going to get k1. And at x equals L, we'll get k2. We also need dw dx. So dw dx, in general, is going to be, well, if we differentiate this with respect to x, we're just going to get 1 over L k2 minus k1. So, so it turns out that if you plug in x equals 0 or x equals L, that makes no difference. It's a constant, it's a linear function in x, so a derivative is a constant function in x. So that simplifies some things. Okay, so now we plug in boundary conditions at x equals 0 and x equals L. So we get alpha k1 of t plus beta du dx, which is going to be 1 over L k2 minus k2 of t minus k1 of t equals a of t. And then we have gamma k1 of t plus delta 1 over L k2 minus k1 equals b of t. Okay, now this is a system of two linear equations in two unknowns, k1 and k2. And I'm going to write it that way to get it closer to matrix vector form. So I want to group K1 and K2 terms together. So I'm going to have alpha minus beta over L K1 plus beta over L K2 is equal to A of t. And then down below I'm going to have minus delta over L K1 plus gamma plus beta over L K2 is equal to B of t. Okay. So it's over L. Oh, sorry, this should be a K2. Because I'm plugging in x equals L. Okay. I was wondering like why the equations were more symmetric, but okay. Gamma plus delta. Oh, this should be delta over L. Okay. All right. So now I can write this in matrix vector form. So my matrix is, I'll factor out 1 over L, because I don't like fractions. So I have alpha L minus beta, beta minus delta, gamma L plus delta, K1, K2 equals A of t, B of t. Okay. So now this matrix vector form, we can use the formula for a 2x2 inverse. And I'm going to leave some of the details to the notes. What I can do is write down a formula for K1 and K2 in terms of A of t and B of t and also these constants. So what we get is K1, K2 is equal to, we have 1 over determinant. Okay, so I have alpha gamma L plus A delta minus gamma beta, and then I have gamma L plus delta A of t minus beta B of t up top, and then for K2 I have delta A of t plus alpha L minus beta B of t. And that's just using the fact that a 2x2 inverse has this nice formula, and that's how I came up with these formulas for K1 and K2. So now your W of xt is completely specified, and then you can solve for V using the same approach as before. Actually, it's exactly the same. Okay, so assuming it was a parabolic problem, the Vt plus Lv equals minus Wt goes there, and then your boundary operators are x equals 0 and x equals L are both 0, and then V of x0 is U of x0, whatever that is, minus W of
So
x0.
in other words,
Yeah.
so how did we get like 1 over like alpha gamma L like?
Oh, from a determinant to this. Now, actually, what I get is, because of this 1 over L, I have like L over something, but then I simplify.
Okay.
Yeah.
Yeah, I just did 1 over L part. That would, I was trying to multiply those two. That didn't.
Oh, I see.
Probably because then you have to divide by L.
Yeah, because when I worked out the first time, I had an L above and below, and just simplified it.
Okay, all right.
Yeah, because you're gonna get an L squared from here.
Right, which
Yeah.
will give you an L, and then you'll have just an L from the for the other guys.
Yeah.
And then that will cancel out with the.
Right.
Okay.
Yeah.
All right.
Okay. Now, let's see. Now that I think about it, if you have, let's suppose you have, if you have a hyperbolic PDE, you can use it. The boundary conditions are the same, so you can use the same procedure to homogenize the boundary conditions. And then if you have like VTT, because if you have UTT and a vertical PDE plus you, you'd have a minus WTT here, and then this initial condition would be the same, but then dVdt at x0, you'd be subtracting off WDT at x0. So it all works out very similarly for hyperbolic problems as opposed to parabolic. Okay.
Those are B's down here under the VT, with the back right there, yeah, those are B's. This
Yeah, the usual boundary condition.
okay. B's and betas.
Oh, right. Yeah, I can see that. Okay. Where, yeah, B0 of U and BL of U are these. Okay. Okay. So for many different kinds of boundary conditions, you can follow this procedure. It'll work. It certainly covers the cases that I was doing earlier. So those are the special cases of this. However, what about Neumann boundary conditions? Okay, if we have Neumann boundary conditions, what are our alpha, beta, gamma, delta going to be equal to? If this is Neumann conditions.
Alpha and gamma will be 0.
Yeah. So.
Beta and delta will be 1.
Alpha and gamma are. Okay, actually. Yeah, they're equal to something. It's not 0. Okay, yeah. So alpha and gamma are 0, and beta and delta are 1. So what happens with this solution formula? If alpha and gamma are 0.
So you get a 1 over
It's a
0.
singular matrix.
Yeah, it's a singular matrix. Okay. Yeah. So also, if you look here, you might be able to see it just easily from here. Okay, so here we just have minus beta and beta, and then with gamma equals 0, we have minus delta and delta. You only have one linearly independent equation when you need two. So this procedure fails. In other words, it is not possible to find a function that is linear in x that will satisfy both Neumann boundary conditions. Why? Because Neumann boundary conditions deal with a derivative. You're asking the derivative to be equal to two different things at the two different boundaries. Well, if you have a linear function in x, the derivative with respect to x would be a constant function in x, meaning you can satisfy one boundary condition, but not both. So, how do you get around that? If you need to satisfy two different things on the boundary, piecewise constant won't, so you can't do piecewise, not piecewise, you can't have it linear in x so its derivative is constant in x. So what do you do instead? Yeah, you just move up 1 degree. So now I'm going to show you how you handle that. So basically, in a nutshell, you do like you would, you proceed like you would from a Dirichlet case, and then you integrate. since I assume Dr. Ding wants to start analysis early, so we don't have much time anyway. Okay, so if we have u dx at 0 is equal to a of t, u dx at L is b of t. Okay. So I'm going to let function f equal du dx. So that means that f satisfies Dirichlet boundary conditions. So f is equal to g plus h, where g solves a PDE with so it solves a PDE of homogeneous boundary conditions, and h is my linear function that satisfies these Dirichlet conditions. And based on a couple examples ago, I guess my first example, it's going to be a of t L minus x over L plus b of t x over L. So that's following the procedure I've outlined before. It just always works out this way in the Dirichlet case. So then I'm going to let u equal v plus w as before, and w is just going to be the integral, and it's okay to let it be an indefinite integral of h with respect to x. So what we're going to get is a of t, we integrate this, we're going to get lx minus 1/2 x squared over L plus b of t 1/2 x squared over L, and that can be condensed. So that's b of t minus a of t x squared over 2L plus a of t x. And you can see if you differentiate that, then it gets you back to satisfy Dirichlet conditions. So it's going to satisfy, so dw dx at 0 and L is going to satisfy the right boundary conditions. Okay. Now, so that takes care of w. But let's talk about v. So dv dt, for concreteness, we'll say ut is alpha squared uxx. Okay. So then vt, which is the same as ut minus wt, is equal to alpha squared uxx minus wt, but then uxx is the same as vxx plus wxx. Wxx is no longer 0. On all the previous examples, w is a linear function in x, but now it's a quadratic function. Now it's a simple quadratic function because now it's going to be constant in x. So if I differentiate this twice, that's the same as differentiating this once, and I'm just going to get 1 over L b of t minus a of t. So it doesn't really change the complexity of a problem any, because, I mean, you knew you're going to have to solve a non-homogeneous PDE anyway. So this is like your big F of xt from solving your non-homogeneous PDE. So you just have to include wxx this time. Okay, so and then homogeneous boundary conditions, Neumann in this case. So in general, we have Vt plus Sturm-Liouville operator L of V is equal to, let's see, minus W minus WT. Yeah. And this comes from the fact that we're assuming that our original PDE is UT plus LU equals 0. Okay, so this is your source term for your non-homogeneous PDE. It's just that in our very first example, this whole thing was 0. In the second example, this was 0, but this wasn't. But in a general case, none of this is going to be 0. Now, if your equation for U has a source term, I'll call it big F of xt, then that's going to show up in your non-homogeneous PDE for V also. So just an extra layer of non-homogeneity. But that doesn't really affect anything. It's going to be there anyway. And then your initial condition is still going to be d of x0 equals whatever your initial data for U was minus W of x0. Okay. All right, I'm going to separate this a little bit. Okay. Although I'm hoping that your notes are laid out more nicely than my board. Okay. So any questions about how to handle Neumann boundary conditions?
So this approach we can use for solving 6.22, right?
Yes.
Because it was
Yes,
minus
it's that kind of
condition.
problem.
Exactly. That's
Okay. Now, the last thing I want to take a look at. Well, as I mentioned, I had another example here of in light of what I've just done. It's actually not very interesting. Okay, but okay. T pi x over pi. But let's go ahead and take a look at it anyway, because we have a little time left, and there's definitely enough time for this. Okay. Well, now I have to be careful here, flipping back and forth between the textbook PDF and the board to make sure it's pointing the right way. Okay, so my last example, PDE is UT is equal to UXX plus e to the minus t. Oh, this is good as a non-homogeneous PDE to begin with. Okay. And then this is on the interval 0 to pi. Okay, so u of 0t is equal to 0. So the first boundary condition is non-homogeneous. And then u of pi t is equal to 1. And our initial condition, u of x0 is equal to, oh, just general f of x. How boring. Okay. All right. So for boundary condition, we can actually use a formula for geometric conditions that I used in the previous example. So it's a of t L minus x over L plus b of t x over L, where a of t is your left boundary condition, and b of t is your right boundary condition. So in this case, what is our w of xt going to be with these boundary conditions?
Just x over L.
Almost. Wait. Yes.
Because
Um,
A is 0.
Yeah, because you don't have this, and then b of t, yeah, a of t is 0, and b of t is 1. So it's going to be x over, well, you can be more specific in L.
Oh, x over pi.
Pi, yeah. Okay. Okay. So that settles that. And we have, okay. Now what's nice about this, boundary conditions are independent of t. So it's linear x, so wt is 0, and wxx is 0. So that means your PDE, so u is equal to v plus w, where vt is equal to vxx plus the same source term. There's nothing else to subtract off from w because wt and wxx are both 0. You have homogeneous boundary conditions on both sides now. And then your initial condition, what should your initial condition be?
Doesn't depend on t, does it? W, that doesn't depend on t.
That only matters for PDE, not the initial conditions.
It would be u of x0 minus w of x0, so it would be f of x, f of x minus f of x.
Of x minus what?
W of x0, so if you plug in zeros.
Yeah. Yeah, so so v of x0 is, yeah, u of x0 minus w of x0
Right.
doesn't depend on t, so you just take w. Yeah. But yeah, if there had been a t dependence, then you would plug in t equals 0. Okay, and that's it. That is a PDE solve for v with homogeneous boundary conditions. And so you'd have your eigenfunction sine nx, because L is equal to pi. Now here's something to think about. When you solve this PDE for v, if your eigenfunctions are sine nx, are you going to get a classical solution?
No.
No.
Because sine of pi is not 1.
Yeah, because, well, it's because of this term right here.
Okay, I said it right.
But yes, that works too.
That
Yeah.
works. Okay, because I looked at the initial conditions and then
Oh, I see.
the boundary conditions that didn't satisfy. Or
Yeah. This initial data will not satisfy these boundary conditions.
oh
Yeah, I'm only talking about the problem for v, not you.
oh okay oh all right. So then, what happens if it's sine?
Because the thing is, linear combination of sine nx would not satisfy these boundary conditions, but that's why we make w.
Okay.
The w satisfies them.
Right.
But the trouble is, let's suppose that f of x is okay. F of x is satisfies the boundary conditions.
Right.
So you think, oh, maybe I'll get a classical solution. So this part doesn't present any problem, but that does. That it's not going to satisfy these homogeneous Dirichlet conditions, not this one anyway. So that's unfortunate. That you're not going to get a classical solution unless f of x happens to have an x minus pi term in there to cancel that out. Which actually I've seen homework problems that do that, so that you think you're not going to get a classical solution, but magically you do. Okay. Any other questions about this
So
one?
for v of x0, what exactly happens? Like, it's sine nx, but then
So you have to expand this in a series to get infinitely many coefficients and so forth. But you're getting a Gibbs phenomenon.
because of that over pi.
Yeah, because of x not being 0 at the right boundary. You have a term that's going from 0 down to -1 when it's supposed to come back up to 0. So
Minus pi over pi.
so you're going to get Gibbs phenomenon in your solution. question? Okay, we got to the end of a chapter. Okay. Okay, so chapter 7 next time.